Well, I'm happy to raise the question that I raised in the comment form, the registration form, which was essentially a Gödelian kind of question. Um, it's that since we are, as soon as we want to achieve some level of kind of precision and definition, essentially forced to use mathematics to talk about our own states and our own interactions with the world, um, however you want to define that, then what what are the consequences for our view of mathematics of this fact that we have to use mathematics to describe ourselves and our um, states as physical systems, our behavior as physical systems, our physical interactions with our environment, whatever it is. So um, I have to use mathematics to describe my interaction with all of you, for example. Um, so how does that bias, if it does bias, our thinking about what mathematics is and um, what it means to claim that um, we are ourselves entities that are amenable, not only amenable to mathematical description, but for which mathematical description is required for a certain kind of discourse, the sort of discourse that we regard as science or as explanatorily productive or as something like that.
If I can not answer that and extend that, if you don't mind, Chris, um,
Please.
it would be whether, so, and I've seen a few talks address this, um, how much, uh, insofar, what is it, how much of mathematics are internalized and used as an extension of our senses versus something that is completely, usable but external or very low bandwidth um, with our subjective, say, awareness and computation. Um, so how do people feel they are on that spectrum? Would be a question I have, and I think it extends what Chris is asking.
Well, I hear two different but related questions there. One is if we take the thing that we currently sort of identify, and I'm no mathematician, so I preface all this with um, I'm saying that I'm just poking around here, but it seems to me that we have a set of conceptual tools that we currently call this is what we think of as math. And so one question is to what extent does that is that applicable to the things that we're interested in here, and what does that mean that we can use it, or places where it fails, right, to capture the things that we're doing when we relate to each other. So that's one question. But the thing that I keep coming to is, do we in fact have a fixed thing that we know this is mathematics and here are the borders of it, and if you go beyond that you're somewhere else, it's not math, it's something else, right? Or is it that our attempts to formalize what interactions between agents and so on is actually stretching math? Is it changing the definition, what the borders of what we thought? So maybe certain things that weren't thought of as part of math then have to become part of math. So is that changing the definition, right? Or is this a fixed thing, and then we can sort of argue about whether it's applicable, and if it's not applicable then we have to pick something else, some other kind of formalism. I don't know what you guys think of that.
Well, I think the definition of, and I should say I'm neither a mathematician nor a historian of mathematician of mathematics um, professionally. So this is only an observation from the outside. But certainly if one looks from the outside, uh, at least how math has been described by humans has changed quite a bit with the introduction, for example, of non-Euclidean geometry. I mean, this was something that no one even imagined up to then. And there are now many kinds of algebras in addition to what was originally regarded as algebra. When one reformulates mathematics in set theory, then it looks different. When one reformulates mathematics in category theory, then it looks different. It becomes much broader. Many things that in earlier formulations looked like distinct entities or distinct systems or organizations turn out to be notational variants. And you say, oh, okay, well, this thing and that thing are in fact exactly the same thing. All we've done is redescribe them in a different language. So it seems to me from this outside perspective that at least how we think of math is constantly changing. That of course doesn't address the question of whether there's some fixed entity called mathematics somewhere outside of our conceptualization at all.
By the way, does that what you just said about a notational, like when we do notice that, hey, this thing is actually the same as this other thing, is that what's the meta level there? With what are the tools that you have to sort of take on board to even be able to make that judgment?
So I would say there are a lot of tools you can use, and there are weak forms or weaker forms or stronger forms of proofs. But this is a very deep discussion. I would say there is not a rule of thumb. You have to make a convincing argument. You can prove by contradiction, which is fun to do, but in the end, you're reasoning. You're reasoning with agents, because ultimately you're going to publish it and you're going to have a community review it. And mathematicians, in principle, are also the first ones to say, hey, I made a mistake. I thought we could do it this way, but after all, I thought about it and I found the loophole. And so it's almost like a continuous dialogue of agents reasoning. I wouldn't say, but then of course you have representation tools that will help you verify, and ultimately you can also have a geometrization, for example, of whatever, of two objects, and then you can see that they relate by some measure, and this ultimately, for example, can work in your favor or in favor of the proof or against it. But I'm with Chris Fields. I think it was a good intuition. But I also ask, why are we asking this question? In terms of what's the assumption is that I want to tackle the assumption, perhaps work it from a different angle. Is it related, for example, with the patterns or with our notion of patterns, because they find expression in our mathematics?
Well, if you're asking me, since I posed the question at first, if you will, one of my major obsessions is the notion of identity. And in physics, that's the notion of identity over time, since we parameterize this thing with this parameter that we call time. But without this notion, physics stops, right? There's nothing to say anymore. And indeed, lots of other things stop. Psychology stops because we can no longer talk about memory if we can't talk about identity. And identity is a key assumption, I'll say, or an axiomatic assumption of category theory, that there's an operator that we call identity. And without that notion of identity, mathematics stops. So I suppose the underlying question, or the question that underlies my question at the beginning, was, what is this notion of identity? And, what does it mean that we try to formalize it in these various ways?
I mean, this is also something that's very fundamental to what we do as well, because as developmental biologists, we really want to understand, what does it mean that you have an embryo which is the same through some period of time, and that things happen to it, but yet this is the thing that's undergoing change. Like, this is a very fundamental, where does it come from, how does it get, how does it come to be, and so on. I will just say that the only reason, so in the motivations that I had for some of this work and this symposium and everything, the only reason I brought up math at all, because again, I don't have a real background in math. The only reason I bring it up at all is that it seemed to me to be I won't say uncontroversial, because obviously there's a lot of controversy, but at least a simpler domain in which to try to make the claim, which some people at least already believe, that not all facts are physical facts. In other words, if you try to do that in biology, it's really hard because it's very complex, and people will say, well, there's some mechanism, you just haven't found it yet. And that's probably always true, because there's always more to be discovered. But at least in math, other people for a really long period of time have already made the claim that there are facts that are not derived from nor changeable within physics. There's sort of this other domain of important information that exists. And so that was my strategy, to say, look, we already know this is the case, or at least many people believe this is the case. And so now we can ask the question of whether some of these things are also relevant for biology, for behavior science, and so on. And we can sort of move on from that foundation. That was my motivation for mentioning mathematics at all, because at least there we have a bedrock where some people already bought into the idea that not all important facts are facts of physics.
I mean, completely. And my question was not to. I agree with you, and it was. I guess the question was to raise assumptions so that we could discuss them. As I find that, for example, Chris spoke of identity. I'm really fond of this topic as well. And it is interesting to think of identity all the time and everywhere. And for example, everywhere, and then all the time, but in no particular place. And these two change. I know this may seem hard in biology, for example, to think of things that do not happen in time, or do not happen, or happen all the time. It's more like it happen all the time. They are the same all the time. And so it's within, for example, a time range. And in development, you see this a lot. You would have an embryo. In principle, it will grow. Stage 22, it will have 36,000 cells as an open embryo. So this happens all the time. And when there's a variation, then we note it down. But in principle, this happens all the time. And so time is, we can express this also from a time-independent perspective. And sometimes I feel that this is helpful, because if there is a structured space of patterns and they're independent of us, then our assumptions of time may be wrong. And this can hinder, for example, our understanding of their development, if they do, right? Because what would it be like to develop not in time? I guess this also ties back with this notion of a memory, that memory is a temporal thing. Because suppose that this structure space of patterns is a space where memory is retrieved from. And so all states that already happened and will happen live there. And so what you have is agents that loop around. And this is hypothesis, of course. And so depending on a local state, they will fetch, preferential points in this structure. And if you want to call this a temporal structure, and there are, of course, physical models, if you will, that could could do this. Perhaps they won't represent the standard model, but they exist, and they're mathematically influential. Then we are no longer speaking of time that passes. You're speaking of agents that are atemporal, and I find this notion interesting. I don't know what you think about it. Another thing, which is we speak a lot of physical facts, and I would like to bring also to the table this notion of relational facts. Because both in mathematics and in physical models, what we are asserting is relational facts. Right?
I can add a question without answering this one, which is how much do you think mathematics and related, I guess, areas or I guess intersections of your own fields with mathematics, how much do you think they are converging or diverging on the mathematical level? And how far, if they're diverging or if it's possible, how much can it stray apart, go very far from the sort of sets of at least axioms, but maybe also concepts and so on, from what you have right now. I'm saying this because I see mathematics as this historically negotiated corpus. So I don't know, from Euclidean geometry to I don't know algebras and analysis and so on, category theory. It feels like, well, at the very least, it's intersubjective, but it feels like it tends towards convergence in most cases. But more so my field or maybe neuroscience, Carl, we see a lot of the connectivity matrices becoming less interesting, and you have to converge towards higher level abstractions to make something the most exciting to me at least. So do we tend towards something that diverges, or does that sort of converge?
I guess depends on what are your parameters. But I find this also, I've dwelled a lot in this notion because I feel it's very important for us and for the research program in general, in this distinction between abstract and concrete. And of course, there are good proposals from logic to to speak of this in terms of properties of sets, but I ask, for example, in terms of a combination. Because when you abstract something, ultimately it really feels semantically, but also if you're going to look under the hood, it feels that you're saying less to address more. And perhaps this also translates to, suppose you have a high feature density. I guess this speaks to the chorus. So feature density means you can distinguish something in your data set or in your model, and that is unique. And so suppose you have lots of these unique features and they don't repeat. And perhaps you would read this as this would be very rich, and you have less redundancy, for example. But suppose the other way around, where you would have one feature that repeats 360,000 times. And so this would give you another kind of ratio, right? Now this is my question for you, to see if you ever thought of things between, or a spectrum between something that is abstract and concrete along these lines. If you were to place something, between these endpoints.
Having seen the different talks and sort of everything that everything everybody has been saying in the symposium, what do you guys think about how many like actually different views do we have here? Like fundamentally, how many different I mean, obviously everybody's got a different perspective on it and so on. But I've been trying to think of, and I'm gonna send out a kind of a table for people to comment on. But I'm trying to think of what the columns of the table should be, the sort of primary axes or something of that people would have different opinions on. In the whole sort of collection about of thought here, how many different views do you think we have, and what are the primary what does the conceptual space look like? Like what are the primary axes where people agree and disagree? Like one, just to give you an example, one basic one that comes up all the time is people say, I agree with what you said about ABC, but I really don't like having a separate realm. This notion, right, that there's people I think like some kind of a monism where everything is kind of in one space, and they really don't like this idea that there's a separate realm in some case. And so we can argue about what does it really mean to what does it really mean to have to be a realm as opposed to just something else, I guess, some weaker form of it. But that's one axis I think where people differ as to what extent is there are there multiple realms. But there's probably other axes. I'd be curious to know what you guys took away from all the discussions as to other like fundamental dimensions where.
I have one other axis, which is, I think, something like physics boundness, being constrained by laws of physics or not, as in a fixed set of rules. And it feels like my talk is on the extreme on both ends of this weirdly, which is interesting. But something about dependency on substrate.
Substrate dependency, yeah.
Let me continue those questions. Let's assume that everything that we want from the representation exists. What then? So what will be the end goal? Because what we are representing is some subset of the real world. Let's assume that we have everything in there. Technically create two worlds. Then what? Or if we have some reduction of concept in that Platonic space, then what can we do with this? What are the best options to do with this?
I would say map it. It depends on the assumptions, right? But if we have agents or if we assume to have agents that, can come and go, then in terms of experiments, as you guys have shown, it is possible to kind of have a source and target map. I guess would be what I'm most interested in.
So for you, the fact that we succeed to map everything that we would like to do or we'd like to operate in the world is a good success of that test, of that theory.
I guess no, but it would give us some truth bounds for experimental means or for managing expectations for experiments. What would be yours, for example, like your end goal?
I will try to predict something that I didn't put there. So there is object A and object B, and object C is infer from all of those. And I know that, but I don't know if my tool can do that.
I'm hearing in the metric of verifying whether it is or it's not a sort of subjectivity notion. You can have it or you can zoom out in a sort of objective godlike view of that, of those agents that Mariana, you just mentioned as well. And I think that makes all the difference, right? So if you switch to also math that we haven't invented yet or that is alien math, so the part where we consider that this is part or not of the subjective perspective that we are holding right now is, I think, important. So yeah, maybe that's another axis for you, Mike.
Yeah, I mean, for me, what I'm really interested in is mapping the space, but also figuring out what is it, what degree of you know, I call it a free lunch, but like what does it actually give you? Because there's a wide range of options. So it might just give you static patterns, like here's the value of E, and that's all you get. It's just like there it is. Or it might give you dynamic behavior or algorithms or compute or you know, what's the range of complexity that you get out of it that you didn't put in, and where, right? And so anywhere from, like, we're doing some things in our lab, like giving bodies, whether physical or simulated, to simple mathematical objects to see like what actually do they encode. If you treat them as behavioral propensities, what do you get? But like more generally, because that has implications for evolution, for sure. I think, to what extent can evolution exploit things that it pulls out of that space without having to take the time to sort of micromanage them, basically, and evolve all the components? Like, what do you get for free, so to speak? You get some stuff, like Stu Kaufman showed us, you get some stuff for free, but I think my suspicion is that's just the tip of the iceberg, and you actually get a lot more. And ultimately, in the lab, we need to be able to say, here are some anthrobots. There's never been any anthrobots. There's never been selection to be a good anthrobot and to do all the weird things that they do. Where do their specific properties come from? Why did we not see this coming? How can we have predicted it? What are the options? What, you know, and what's the relationship between the thing you make and the stuff that then comes through? So if we tweak, you know, can we tweak certain things about the anthrobots if we want other types of patterns to come through? So that's what I'm interested in, is what do you actually get, and what's the relationship between the interface that you build, the physical interface that you build, whether that be technological or computational or biological or some combination thereof, and then what it is that is going to be that's then going to come through that you had no idea about.
Yeah, I mean, one of the things that I've been thinking a lot is exactly the work that you do, and precisely this mapping. It seems to me that mapping based also on your experiments, and of course under the assumption that developmental states are, you know, are pulled in, or whatever it is that you want to call, then this mapping can also allow you to, in very practical terms, to address, for example, regenerative procedures at late stage, you know, so you don't need to catch something early stage because you already know how to pick up that pattern in case there is a, let's call it, I would call it topological defect, but in your sense is a developmental stage. And this is why I find the mapping really relevant. And of course, it might not be the best approach, but I think when you speak of free lunches, these, I would say, these are the free lunches. like the low-hanging fruit that we could use. But also this thing you speak of, if in terms of evolution, of this tendency for growth in form, and I've been thinking a lot about it, and it seems that when you speak of perturbations or abrupt perturbations, things that were unforeseen so far, that then output these developmental novelties, like the anthrobots, or I'm very puzzled about the tail onto the flank. Like, why not the tail? Why not keep the tail? It's so much cheaper. Why not reject the tail? Cheaper. Why build the limb? It seems like it's the most I know your assumption is that it's more helpful, or that is more useful, but I feel that sometimes I wonder, like, why. It just feels that, for example, a limb is more complex in terms of edges than the tail, right? And there are in physics, it's, I guess you would call it relational mechanics. There are some proposals exactly in these terms, where where whenever there's a chance, let's go for partition. Let's just go for something that is different, that has, and this would be some sort of, I'm speaking in very broad terms, this would be the measure of complexity. So complexity is just a relational measure for between you and your neighbors around you. I like it.
I mean, it's a very interesting question, and I don't want to like dominate this thing. So please, Yvette, Juan, Brian, Carl, please chime in. But this question of at what point does the thing give up on the standard implementation and sort of shift over to something else? Like there's a standard. You can call it an attractor, but I don't think that's all it is. There's a standard version of an embryonic body plan that it will try to hold to. If you deviate it, it will work pretty hard to get there. And if you put on an extra tail, it will try to make it a limb and things like that. But at some point, you can push it so far that it basically says, forget it. I'm now an anthrobot. I'm not going to try to make a human embryo. I'm just gonna, this is my new life. And one of the ways that we're actually trying to address that is to look at stress markers, because we have a project looking at stress, systemic stress as a measure of distance to your goal state. And there are scenarios where and basically the stress the tendency to try to reduce stress is what pushes you to get back to where you need to be. So we're actually like interested in this question of, okay, are Xenobots and Anthrobots, are they stressed out about being those things, or at some point do they, that's the new set point, and so now being a Xenobot is my set point. I'm now a great Xenobot, so now my stress can fall. Like that's an experimentally detectable kind of thing, and so we're actually doing those measurements. So that's one way of doing it. But in general, I think that's a great question, is at what point does it, and I don't think it's utility or anything like that in the, at least certainly not in the short term. Yeah.
So I misunderstood.
Well, yeah, I don't know. We don't know how a lot of these decisions are made. Like there's so much that these systems will tolerate and try to accommodate to still get back to what they need to be. But there are also scenarios in which they just flip to something else. Carl, please.
I was trying to lower my hand. Good. Yes. So, yeah, some wonderful questions there. I wanted to pick up on this notion of stress and attractors, but try to frame it in response to some of the questions that have been rehearsed. So let's go right back to Chris, a question about the nature of maths. And I noticed that he used the word dialogue. There was also Mariana's notion of discourse, and then we had Olaf's negotiated corpus. I think all that speaks to maths just as being a particular kind of co-constructed language that has an enormous amount of explanatory power in terms of accounting for things accurately with the minimum complexity. And in so doing, I think that the question about convergence touches upon, Mike, what you were asking about. Is there something else, or is this just another version of the same thing? And I call, if you pursue the the notion that the right kind of language and the right kind of maths is going to explain everything as simply as possible, but no simpler, then you're looking for that exactly for that convergence. And that, I think that speaks a lot of what people were saying in terms of it, your maths being a continual process of basically model building, a co-constructive model building. I think that was a sort of a theme which caught my attention. The notion of identity, in my world, that would be self, and it would be the self you find in self-organization. It would be exactly the same thing you find in information theory in terms of self-information, right through to self-evidencing under the free energy principle. And I mention that because that stress, I think, is mathematically simply the self-information or the implausibility of finding this kind of thing away from its attracting set. So coming back to the attracting set, I think that the notion of a pullback attractor probably has everything that you need in order to accommodate all the questions that I've heard thus far, and that really commits you to a particular kind of maths. And it probably wouldn't be maths; it'd be physics. But certainly, mathematically framed, you would be seeking out for that convergence that people were talking about, the kind of maths that allows you to explore all of the issues that we've been talking about, and also provides that point at that nidus of convergence that that will enable a certain consensus. And it strikes me that the notion of an attracting set has everything that you need. Think about Mariana's questions about things that recur in time, memory, persistence in time, having characteristic states. You can express all of these things um, in terms of attracting sets. So you just need the physics of attracting sets, and that's just basically pullback attractors. And within that, you can now define self. So you don't need to be axiomatic. You can just say, look, let's assume the existence of identity in the sense that there is a self that is constituted by the attractor. And I think everything else follows. And just to bring that to closure, I think that the stress is just a measure of the distance or how far outside your attracting set is. And what will happen is you'll go back to your attracting set. So that was my breathless summary of the thoughts that were induced by the conversation.
Brian.
Oh, thanks. So yeah, I just wanted to add, like, from this notion of perturbations, and I think like one of the issues of Platonic spaces that I always reconcile with is whether this is all observer dependent in some sense. And I think the notion of perturbations is a nice way to think about making the observer aspects as weird as possible, potentially. Like in the computational realm, you can do this. And I think Mariana talked about this notion of experiencing time, and the aspect that maybe you can actually have agents experience time in a very different way than we experience time. So we actually already have these in the AI space, like they're called diffusion models. And if you've ever read like the Ted Chiang stories or like seen the movie Arrival, there's this kind of gap between how we personally oftentimes see time in a linear fashion, but diffusion models in the sequence space, they see time in a completely different way where everything appears at once. And when everything appears at once, you can imagine that this is something that diffusion does, where it looks at like generating the entire story everywhere at once. So we're now exploring this because we're interested in whether these same systems learn algorithms that we're familiar with, or they learn completely different algorithms in the space of, like, for example, games like Sudoku and things like that. So I think like this notion that we should make the observations as different and as weird as possible. And that's the way to actually at least hope that, I mean, I guess we're always going to be locked to some notion of observer dependence, but we can generalize that observer dependence further and further out.
That's super interesting. Can you say any more about that? Like what are you actually doing with these diffusion models?
Oh, so yeah, we are actually training diffusion models to play Sudoku, because Sudoku is one of those games where, I mean, it actually has a lot of computational advantages too, because it's an NP-complete problem. But the idea that the algorithms that we usually use for Sudoku is if you play Sudoku, like this causal structure of, okay, let me find the least constrained square, and let's go forward from the the most constrained square to the least constrained ones and solve the puzzle that way. The diffusion models, if you actually train a diffusion model to solve Sudoku puzzles, they solve it very differently. Actually, we don't quite understand how they solve it right now, but they definitely don't choose the obvious strategies of like, oh, let me march down the least constrained square to the most constrained square to the least constrained square. It's actually like something that almost feels random right now. We haven't done enough analysis on this yet, but like the way it solves Sudoku could also lead to new algorithms in that space. And maybe the time complexity of those algorithms are actually very different than time complexity of algorithms that we have created in that space. And again, because it's an NP-complete problem, there's a lot of computational complexity analysis that we could potentially do in the long term from this. So we're just training diffusion models on things that we already kind of have an algorithm that we know works, and seeing what the diffusion model discovers as a different algorithm. But I think this is also worthwhile studying in the language space too, because there's diffusion models in language now. So you could also look at the algorithm that diffusion models acquire and the representations they acquire by training on the sequences that we believe are, generally temporally linear.
Yeah. Well,
hi, sorry, I don't find my e-hand. This is very strange. I've been looking and I can't see it, so I apologize for just jumping in. It's my first time at the meeting, so I wanted to say hi to everyone and thank you for the invitation. I will try to join now regularly, that my schedule is a bit more organized now with my teaching, so it doesn't interfere with that, so that's good. Maybe I just wanted to quickly introduce myself. I'm a physicist and I work in the interface of quantum mechanics and general relativity. And I'm just going to be listening for a while and then see when I can chip in with something more meaningful. But maybe just an interesting connection could be that one of the things that I'm interested in is the interface between the classical world and the quantum world. And I tend to see these as two different realms. Maybe this is just like a perspective that can be helpful, because at the end of the day, you could say, well, it's all part of one whole, so why divide it? But sometimes these divisions can be useful. And because the sort of thing that I'm starting to see is that like the classical world emerges from the quantum world. So, I mean, they're like different realms in the sense that they follow different rules. But they interact, and that's important, because in the lab we can go and we can prepare a superposition of an atom going to the left and to the right. But we also see like, well, what I'm working is on the emergence of mass from, let's say, rules in the quantum world. And some of the things that I find that has made difficult our understanding of the quantum world is that we try to put a lot of like the classical world into the rules of classical world into quantum world somehow. So anyway, I was thinking just about some things that you've mentioned, like what's physical in a way, what's physics, where do you draw the line of what's physical or not? And we have a lot of arguments about that within quantum mechanics, because even within our community, some people argue that quantum mechanics is physical, and some other colleagues say, no, it's just information, and it's just kind of some sort of mathematical tool to make some predictions, which I don't even understand very well what that means. But because we haven't understood quantum mechanics well yet, it's still very debatable what is the question of what's physical or not. So I think the question about different realms and what's outside the realm of the physical, that is definitely something that interests me very much. And well, I'll just say, it's a bit just saying hi, and hopefully I will be able to contribute later on.
Great, thank you.
It was lovely hearing you, Yvette.
Thank you.
And I agree. I find myself rarely using these terms of physical, and I don't find them very useful. And there are a lot of mathematical or mathematicians that are contributed immensely to mathematical biology, which end up contributing a lot to quantum theories or field theories because of this, because the morphogenesis, in a sense, has this sense of pinpointing the questions of the first mass, and how mass behaves at different scales. And we have all these effective theories and models that have predictive power, but then on the other hand, we cannot find the physicality for them. The temperatures are off. They don't reproduce anything but that behavior. I don't know. It was lovely hearing you.
Oh, thank you very much. Yes, I'm excited about joining this discussion because thanks.
Can I
Brian,
go way back
go
to
ahead.
one of the previous topics, which had to do with what we're actually trying to achieve with both this discussion, but with science in general, mapping our space in general. And in a sense, one can look at it from two fairly different perspectives. One is the perspective of trying to predict what we will see, and the other is from the perspective of trying to characterize what we won't see. And if you think of mathematics as a formal system, or if you think of physics as a set of symmetries, a postulated set of symmetries, where everything else, everything beyond the statement of what the symmetries are, is a relative fact of the sort that Mariana was describing earlier, then what comes out of those two ways of proceeding is a list of things that you can't do, or a list of structures that don't occur, or that don't make sense. A list of no-go theorems, right? Like Gödel's theorem, for example. And everything else is, sort of subsumed under T.H. White's law of the ants, or what Gelman called the totalitarian principle, that everything not explicitly forbidden is mandatory, right? If you can't prove that something won't exist, then you're going to bump into it somewhere. So it's a possible pattern, or a possible attractor in Carl's terms. And it may be entirely unclear how to construct that attractor, but in the absence of a proof that it's impossible, you can expect it to be constructed somehow. But that's a very different, very negative way of describing what one is trying to do, to say that what one is trying to do is characterize the impossible.
Carl, please.
Yeah, so I thought it was an excellent point. I'm just thinking of what a more positive take on that. You could invert the problem and just assume that we want to characterize systems that can exist, and then work from there. And in that sense, what you are doing is saying that if a system is characterized by these characteristics, then it can't be over here in some state space. And that's just the surprise or self-information or stress that we were talking about before. And that comes for free with just writing down a density over states that can be occupied. And of course, there are many more ways of being dead than alive, and it's a very small attracting set that remains there. In answer to that question, well, the previous question I would have liked to have answered before. In my world, the utility of having the right kind of maths means you can simulate things in silico. And if you can simulate things in silico, then you can now do forecasting. You can do now scenario modeling interventions. You can sort of test hypotheses about perturbations to the system. And this becomes really practically relevant, certainly in things like computational psychiatry, where you start to simulate people, for example, and when their, say, sense making or decision making goes wrong, or any sub-organizing system like climate, financial services, fintech, and the like, getting the right maths and the right kind of self-organization in play opens up a whole world of practical and really important ways of intervening and testing hypotheses via simulation. The other application, of course, is you can actually test hypotheses about the unknowable mechanisms of the system that you're interested in because you can't observe it directly. So now you can start to test hypotheses about the mechanisms via because you've got the right simulation test bed. And then finally, if it's all working, you can put it into a diffusion model and make artifacts, and you can sort of then move into the world of autonomous vehicles, artificial intelligence research. So actually using these the right kind of maths to drive and to create artifacts that somehow embellish or endorse our ecosystem and the things that we actually play with and use. So I think that, practically from my perspective, that it's really important to get the maths right, because once you get the maths right, you can now answer all sorts of really important questions.
Could I ask about what you guys think about the distinction between simulation and explanation? Because this comes up in biology in the following way. I'll say, look, we need to understand why this thing is doing that, and people say, well, it's emergent. And I say, well, what does that mean? And they say, well, what it means is that if we were to simulate the sort of micro rules that are driving it, this is what we would see, and it's a regularity that holds in the world. That's what it is. I say, but what does that mean that it's a regularity that holds? And what they mean is if we simulate the low level rules, then out it will come, and we can sort of show that that's the case and get a sort of catalog of these things, and that's that. So I'm interested in what the relationship is between being able to simulate it and thus show that yes, in fact, that is what happens, versus understanding what's going on. And I was sort of thinking about an extremely minimal case of this, like the glider in the game of life, right? If what does it mean to understand the glider? Let's say the rate at which it moves or the angle at which it moves or something. And so what somebody can very easily do is show me the 4 steps, right? The cycle of the thing, moving over, and we can all agree that, yep, sure enough, with the physics of this world, that is exactly what happens. Nothing more to say about that. But have you explained it or have you simulated it? Because with enough simulation, it seems like we could get the answers and maybe not understand much of anything. I don't know. What do you all think is there a distinction, and if so, what is it?
So for me, I think I have a very pragmatic distinction, which is it's a continuum explanation and virtual simulation. But if you can accelerate the simulation to a point where it doesn't have to run in real time or doesn't have to run in reality in some sense. So the idea is that explanation allows you to skip a lot of steps. It allows you to go way faster, way more forward than maybe a simulator would be if it had to simulate the entire universe to get to the same point that you want. So in the cellular automata case, it'd be like, I can predict gliders ahead of time without actually running all the intermediate steps that require a glider to be formed in the game of life.
Yeah, I think someone just said that before, and I think Brian, you said it too, which is about just short, compressed explanation. So the simulation is a shorter explanation if the usual route is much longer in terms of time and space and compute or energy or whatever you want. That makes sense to me. And that's in the same sense that I wrote this thing about LLMs being frustrating. It's because you put so much data and compute into it that you can't possibly think that this is very truly highly intelligent because you invested so much in it. What is impressive about intelligence is that you put not much and you get a lot, which is how you phrased this, right, Mike, earlier. Math is impressive because you put something and you get so much more out of it. So I think there is this notion of compression and efficiency that we expect, and otherwise we are frustrated.
Could I just endorse that? It reminds me of arguments for universal computation, inheriting from, say, Kolmogorov complexity and compression. So when I hear compression, I hear sort of maximizing the likelihood of your model. And I mentioned that, Mike, for Mike, you can look at simulations basically as a glorified statistical test. So when we do a t-test and we're asking a question about the mechanisms or our hypothesis about the causes of some measurement or some data, we are doing a simulation. We are building a little generative model, a general linear model for the t-test, and we're simulating what could have caused the data, and then we're identifying the best hypothesis. So when I talked about simulations, I wasn't talking about you know, using maths and computers to reproduce behavior. I was talking about simulations used as a statement of your hypothesis about the underlying cause-effect structure that generated those data. And then you can compare different simulations, i.e. different observations or statistical models, and then you can quantify the evidence for your hypothesis here and hypothesis there. That's what I meant by being able to answer questions in the good old-fashioned scientific process. But to do that, you've got to have the right kind of model, and you've got to have the right kind of maths that underpins that model, which is an open question and an ongoing challenge, which I'm sure we're all contending with.
I'll throw in a different way of answering that question, which is to say that a simulation may reproduce some effect that you're interested in, but it doesn't force you to change your conceptualization of the effect. It doesn't force you to change your language. Whereas a really good explanation often forces you to change your concepts. So, for example, go back to 1900 and consider the question of how there can be atoms, right? Why are there any atoms that are stable? And the going theory back then was that, I mean, the difference between protons and electrons was understood, or between the nuclei and the electrons were understood. I mean, that language hadn't been invented, but it was known that there was positively charged stuff and negatively charged stuff. But it was also known that if the electrons actually moved in the atom, they would radiate away their energy and the atom would collapse. And so there wouldn't be any atoms around, no stable atoms. And so that was the question that the Rutherford model ended up answering. And Rutherford's point was that electrons don't move, that electrons can have particular energies, but they're not moving, so they don't radiate unless they change their energy in very precise ways, and they can only change their energy by finite amounts, and in fact, only by particular finite amounts. And so they'll only radiate by these particular finite amounts. And that radiation is not due to motion. So Rutherford's picture introduced a radically different conceptualization of what an atom was. And that's why it was a good explanation. It made sense because it got rid of an entire problem, the problem of radiating the energy away and the atom collapsing and being unstable. But to get rid of that problem required a conceptual change and an abandoning of intuitions about motion. So I would say a really good explanation is something that causes us to abandon some intuition.
I like
And
that a lot.
simulations don't do that.
Yeah. I like that a lot. I think that's really good. So okay, so it sort of evaporates certain problems. It inevitably raises new ones, and is that okay? Is there some sort of ratio? Like I've seen reviewers' comments on papers where they say, "Well, this raises more questions than it answers." I'm like, that to me seems like that's what that's what we're supposed to do, but maybe not. Um, so what should be the ratio between the problems that you've evaporated and the ones that you've now unearthed?
Well, I suppose the new problems should be more interesting than the ones you've evaporated.
Well, you can sometimes you solve a problem by switching languages, right? You create a new field sometimes in nice successful cases, I guess. But you can always backtrack into the other language, which is what happens when science splits, and science is very split, the way I see it. That's why we have hope for things like category theory and things that bridge those between the fields, right? But essentially, yeah, you have one cake and you eat that one or the other one, but you can't eat both. You can cash them out both at the same time for now until you unify. Isn't that I don't know how happy people are with this sort of linguistics kind of perspective of things, but that's how I usually see it. But you can backtrack. I guess you can always speak the other language, and oh, now we solve the other problem.
If it's a common language, though, the ratio that Mike was asking about would be a log odds ratio in Bayesian statistics and post-Popperian hypothesis testing. It would be a Bayes factor, just basically the relative probability of these data measurements or observations um, conditioned upon this simulation or that simulation, where the simulations embody your hypothesis, your mechanistic explanations, your conceptions. So the art of being a good Rutherford or a good scientist is to uh, exactly deny your intuitions, your prior beliefs, and explore other hypotheses. Then you put that hypothesis in some converged maths and make it into an observation model. And then you evaluate the likelihood of your data under that observation model relative to another one. And indeed, you may find yourself going back to the null hypothesis. And if you commit to classical or frequentist statistics, then a failure to reject the null keeps you well stuck. But if you use more generic um, model selection approach based upon that Bayes ratio or log odds ratio, then that, I think that sort of provides a really nice space in which you can think of the scientific process as elaborating new hypothesis spaces. And then you've got the technology to evaluate how you proceed, how you sort of take a path through the space of hypotheses. The challenge, of course, is to elaborate new hypotheses. That's and ultimately you come back to sort of natural selection and evolution and the law of requisite variety and the like to elaborate those. But notice that depends upon having converged maths. So you can take two concepts or hypotheses or models and simulate data generation under these two hypotheses with the same, in a comparable way. So you can evaluate the probability of your data, given these two observational concepts or hypotheses. You couldn't use category theory to do t-tests.
Yeah, I'm not very good with this with the term simulation or But I really like breaking assumptions or trying to think, cross the borders in terms. And I think the first time I heard your framework, Mike or Tame, I thought it just gave so many disciplines a fresh set of tools, if you will, or even if it's thinking tools. And I've been thinking a lot about them for our research program. Because when you have, let's say, a technological approach to mind everywhere, and you try to define, okay, but where is everywhere? Where is the limit? Then we may find ourselves with this opportunity to do these experiments now outside of biology. And this is no easy thing to conceptualize, of course. And I feel that I've been working very much at the limit, or at least at my capacity, because it requires this interpretative competency to go into all these different fields and try to match the framework and also behavioral competencies to things we wouldn't otherwise, or to fields and in terms we wouldn't otherwise do. And it's a real mind bender. I don't know where you are all regarding it, if you have thoughts also concerning this aspect.
Well, I think one thing that the framework uh, requires of us is to uh, abandon this notion that we are special in a very particular way as cognitive beings, and to allow ourselves to consider all sorts of other systems as cognitive beings. And that's, in a sense, deeply deflationary. I'm not sure whether that's what you really mean by it being a mind bender, but that's what I see as the primary challenge of it.
Yeah, I'm not sure why I said mind bender, but now I like that I said it. I guess it's more, I personally, and I think it's a good thing. I don't know how to evaluate the behavior of humans, their intentions. I do not know, and I find it a bit puzzling. And so it is easier for me to see from Mike's perspective. There's a technological approach to mind everywhere, and there are ultimate preferences, if you will, and it's easier for me to see it in animals. But now transposing these classical conditioning techniques that you would see behavioral changes in animals, but then posing this into mathematics or even to electrons. If we were to classify their behavioral profile or their preferences or their skills, this is what I've been calling what I said, it is a mind bender. Because of course it seems very conceptual and it has absolutely no use, but actually I feel that through TAME and multi-scale competence architecture, we actually then have at least a way to transpose these conceptual ideas about agency in other kinds of spaces and then test for them. I guess what I mean by this is, if you have an observation that an object X always behaves the same way, is this non-interesting, or is this an extreme preference? A preference X would not let go. No matter what you do, X will do that. And I think this raises a lot of questions, and a lot of good questions, because maybe there is something that X likes more, and we can test for that, and that suddenly X has two behaviors, and you don't have the same paradigm you had before. I'm not sure.
Well, I think there's another way to look at that, actually, which is perhaps equally interesting. That if you look at X and X only has one behavior, then perhaps that is mostly reflecting on your capabilities to look. And that X may be doing all kinds of things that you can't see because you're choosing to observe it only in some particular way. And it may be that the way that you observe it is what leads you to call it X, as opposed to something else. And that your method of observation is what, I mean, in a sense, it's inevitable that one's method of observation is what one uses to cut up the world into systems with boundaries or Markov blankets or however we want to describe them. And then that automatically restricts the measurements that we can make, as well as automatically restricting what aspects of this, automatically restricting the aspects of the system's behavior that we can regard as behavior, because it gets encoded on the boundary that we have identified.
Yeah, I completely agree. And I guess this poses another question, which is, suppose you got a new set of goggles, scientific goggles, and you have a new framework, and you see that X always chooses something in this space. But now you found out that it has a different behavior in some other space, but it behaves quite similarly. It has one preference in that space, and you keep doing this over and over. And my question is, would this be, how can we state this preference? Or how can we pose things in other terms than, for example, perturbation or stress, more in trying to figure out what they want, what would be beneficial for them, instead of trying to use them? Because I feel that this is something, and of course, it brought us so far. But I wonder if we are to shake all assumptions, and if we are to take these frameworks, I think even on an experimental means, it feels interesting to think, what would they want? Because then perhaps if we have a different kind of behavior, I don't know, we would have a little bit of more ground truth to judge such behavior. But I mean, I agree with everything you said. I don't think this is a simple problematic. I think it's a very interesting one.
Could I ask, you're using words like preference and want, which I like, because I talk about prior preferences a lot, but it does sort of anthropomorphize things to a certain extent. So you know, it sounds to me you're talking about things that conform to a variation principle of least action. They have the most likely path, and that path is the path they prefer. And how much do they deviate from that sort of path of least action? And it makes me wonder whether the answers that you would supply, which could be articulated in terms of preferred paths and wanting to get to the end point of the path of least action, are they scale dependent? So I want to ask Chris, does let's just take two extreme scales. Let's take the electron and the moon, both of which have lawful behavior. Do either of those want or have a preferred course of action or a preferred behavior?
Well, we certainly model them as if they do in terms of least action principles and so forth.
So I'm just trying to get at the mind bending thing. So why doesn't that apply to you and me then?
Oh, I'm not sure
Is
it
that
doesn't apply to you and me.
good answer? Yeah, yeah. Well, I'm trying to get at the sort of the sort of the mind bending issue, because you can certainly talk about the moon having a preferred trajectory or path, and certainly likewise an electron or at the quantum level. But what is special about the kind of self-organization that Mike is commits his life to trying to understand, and indeed this Platonic series is trying to address.
Yeah.
Why is a principle of least action not sufficient, or is it?
I mean, I don't know about the moon and all, but we've been looking at it in very minimal computational systems like the sorting algorithms that we've all talked about. And I don't know actually if so what we've observed for anybody that hasn't seen it is basically that these are simple deterministic algorithms. Yes, they sort like they're supposed to, but it turns out they also do some, like as we were just saying, if as Chris was just saying, if you look at it from a different perspective, which hadn't been done in all the years that people have been studying these things, you actually see something quite differently. And you see them doing some other stuff that is very surprising. And I don't know if the right way to look at that stuff is as also goals that they're attempting to achieve via some least action thing, or whether that whole framework is limiting, and maybe that's the part that's exploration and play and these other things that are not actually goal directed behavior. Maybe that's the more interesting volitional sort of play aspect, where the sorting is what you forced it to do, but in between, sort of in the spaces between that, there's some stuff that for whatever reason the system likes to do. I don't know if these are all appropriate terms or not, but I think we can start to look at some of that in these very minimal models. I don't know if that's more minimal than the moon or less. I'm not sure what you guys think, but it seems very minimal because it's deterministic. We have control over all of it, and yet there is some stuff that's happening in the spaces between the thing you actually wanted it to do. And so this is still something that I'm playing with different frameworks. That maybe it's another set of objectives to optimize that it's doing, or maybe that's the exploration part, the sort of intrinsic motivation, which then scaled up is what we see in us, and so on. Like maybe that's the simplest version of what that's what that actually looks like when you push it all the way to the left of the spectrum. That's what it looks like. There's something on the chat. Oh, yeah, Santos just wrote on the chat that maybe the ingression of the abstract into the physical maybe also follows a principle of least action. I actually think that's quite reasonable. I've been thinking about those ways too. Like the sort of really simplistic way I started thinking about that is that these things in that latent space are under positive pressure. That basically you don't have to work that hard to get them to ingress. Basically, if you make an interface, there they are. So they're like in some strange sense pushing out. That's there's a baseline pressure in which they are going to get into this world. But there may be a more sophisticated least action kind of thing that could be used to describe what actually shows up relative to what interface you've made.
Yeah, I've been looking into it because it's hard to discern if what we call or what we observe as a principle of least action is it's because of the configuration of the space, or it's because it's the best transportation mean, or because it's the most effective path But you have this notion of path, transportation mean, and then spatial constraints that can just be if the boundary is a space, and where all boundaries meet. But this to say that in itself, it gives us a lot of predictive power in other areas. But I feel that for us, for example, tail and not limb, or limb and not tail, if you model it from, some sort of like, there's no minimization of surprise there. Quite contrary, and so I feel that in these cases, least action would serve us as to model the path of whatever it is that ingressed, for example, according to how we model the space, but ultimately would not tell us the content. And I'm very interested about the content. What is being ingressed? And so not in terms of the geometric path, perhaps not even in terms of the conflicting dynamics that may happen at ingression, because suppose X and Y both want to ingress, who wins? More of the content. And there is, of course, very good mathematical constructions to do this, and you can kind of glue them all together, and then you can look inside and you can see. But I'm pretty sure, what would we do with it, with the content, for example?
So you said again, what would we do with the what?
With the content. Suppose that we can not only model the ingression, we have the path, everything, but we also have the content.
I think we're then back to the utility of having a simulation. And when you've got the simulation, you can now do intervention experiments. You can now test hypotheses. You can now ask questions about what would happen if I did that? How would it respond in this context? What are the emergent behaviors, and deploy them in the way that we've been talking about. I think just from a physicist's perspective, not that I'm a physicist, but from a physicist's perspective, sort of numerical analyses are the thing that get at the content, and they reflect the application of a principle, where a principle is read from the perspective of the physicist as a method. So if you get the right principles, the right maths that equip you with the right methods and tools, then you apply that to ask questions about the different content under those principles. Does that make sense?
Yeah.
For example, why a tail and not a limb? That's just an expression of a path of least action expressed at an evolutionary scale, where you now read natural selection as a path of least action, where the Lagrangian is adaptive fitness, and in fact adaptive fitness can be, in this instance, equated with the marginal likelihood of finding this kind of phenotype in this eco niche, and the marginal likelihood is just the negative self-information, which is
I agree with you, and it makes sense. And if it wasn't for this research project, I would not be debating this, but now I find it very useful to debate it, because why, and phenotype and all of this, like, why? I feel that our models are very good at predicting a lot of things, and we can do a lot of things with it. It is true. But why is it not a preference of some pattern that we don't see, with whom we can obviously interact? Hypothesis. Because if we see it like this, then we have the possibility to interact. For example, on this question of content, if we have the content, for me, what we could do is do a code book, and we can communicate. And perhaps this is absolutely bonkers, but in 2 years, maybe we have a new telecommunication system, because this was a big nonsense, but something nice came out of it. And it feels really good also to be able to speak about this with some. What do you think of a code book?
So, I mean, I would add, which I think maybe is compatible with what you're saying. There's the third person perspective, which I think is what Carl just very nicely described, where you look at this thing and you sort of you sort of see, okay, here's I'm gonna model it. I see this particular pattern is coming through. I'm observing it in a kind of a third person perspective. But I think there's also the other end of it, which is, what does the world look like from the perspective of the thing that's coming through, right? And close to that is the issue of, wait, we are also potentially fundamentally patterns that are now manifesting through whatever interface, right? Biological and so on. And so when we talk about communication and so on, I think there's a whole research direction here, which is different and harder than typical third person science, which is to look at the agency of the patterns themselves and of us as also these patterns, and the communication that takes place conventionally in third person through the physical world, but also possibly directly lateral. I mean, this is what some mathematicians have said to me, and maybe what Darwin meant when he said mathematicians have a different sense. This idea that they sort of perceive, like some of these, when they perceive mathematical truths, it doesn't kind of dip into the physical world and come back. They're not doing experiments, they're not making observations. It's sort of, they have some other interaction, right? And so you could imagine a direct interaction between patterns from that space. And I mean, obviously this is very weird stuff, but maybe that also is an aspect of the communication when we start looking at it from the perspective of the thing that's coming through, not just from us evaluating as passive data, like here's the thing I see.
It wouldn't be weird from an evolutionary psychology perspective. I mean, you're talking about cultural niche construction, sort of, new wave, the Markin aspect to evolution. If we have co-constructed a culture of good maths, and good just simply providing the simplest or least complex explanation for everything, and that can be inherited from generation to generation, then that's a perfectly that is a perfectly consistent process with a path of least action, where action in this instance has some sort of elevated meaning in the context of evolutionary psychology, Devo constructs taken into the cultural domain, which brings us back to the convergence and the discourse and the negotiated corpus of or calculus that we commonly accept as the right kind of maths.
Yeah. Well, yeah, thanks for bringing that up. I guess it is true. I'm no authority, of course, but there is a lot of love and devotion, I would say, that and almost like even sacrifice that goes into doing maths. That I guess perhaps it is a bit different. But I would also say that one setups experiments, and then it's a bit of like pen and paper. What if there's a lot of what if, and then you state the problem in a different way, and you use a different example, and I don't know if it's the same for everyone, but it feels there is some proportionality between this love and this devotion and this, but at the same time, this plain curiosity, that it's never really about you. And then I don't know if it's the same for everyone, but it comes to you, and it feels the more you put in terms of being alone and thinking about the problem, then the more it comes. Again, I'm no authority.
Yeah, I'm looking forward to adding. I didn't get it. It just hasn't been scheduled yet, but there's a couple of conversations coming soon for this symposium with musicians, because I've had a lot of outreach actually from people who have said, are not scientists or mathematicians. They make music and they've been watching this stuff, and they said, oh yeah, well, this is what it means when this is what it's like when a particular song makes itself known to you, and and it comes through, and this is like that their creative discovery process. I find very interesting, and to compare and contrast to what we all do. So yeah, I think that'll be a nice addition from if I can get I'll try to get hold of some more artists and people in that space.
Yeah, sometimes I've been discussing also kind of informally with some to ask about this ingression, exactly treating, I let them talk and I'm trying to map whatever it is that they're saying to this ingression mechanism. And sometimes I feel, I mean, of course, perhaps you can model it with priors, but there are things that are novel, like in morphogenesis. They've never heard before. They believe they've never heard before. It is soon. You've been recording it.
It hasn't happened yet. It will be recorded. I'm trying to set it up. It's just yeah. I thought our schedules were weird, but theirs are even more challenging, apparently. So, but we'll make it happen.
If I can make just one more comment from a physics perspective, we always are moving or are able to move back and forth in physics from a theoretical stance in which the world has been divided up in some particular way into systems that have certain internal processes and hence interaction capabilities, which we can describe as observational capabilities or action capabilities, if we want to use that language, or just treat them as interactions. We can move between a perspective that cuts the world up in one way to a perspective that cuts the world up in some completely different way. And moving between those perspectives changes all of the interactions that one describes between the components that we've made by the cutting up process. But it doesn't change the assumed behavior of the whole system.
Mm.
So whatever model is constructed has to be consistent with the underlying principle that if you just erase the boundaries, take your pencil and erase all the lines you've drawn, that nothing has changed. Right? So I'm trying to get to this point of to what extent does our perspective in which we each view ourselves as bounded entities bias our thinking about how patterns interact. Given that if we do, take our erasers and erase these boundaries, we haven't changed the patterns. We haven't changed the overall pattern. We've just changed how we describe different pieces of it interacting by creating the pieces. If we don't have those pieces, that interaction, of course, doesn't exist, but that doesn't change what's going on in the background. And so when one thinks that way, the question of what does it mean for these to think about patterns interacting takes on at least a different flavor, because we describe it in a radically different way when we think of some big box with a bunch of stuff happening inside of it versus the big box being cut up in a lot of little ways, and where we think about these little entities that have to exchange information across their boundaries.
Chris, is that not easily resolved just by picking a particular scale? I mean, you're talking about little boxes in big boxes, little Markov blankets within a big Markov blanket. The only difference being there always has to be a carving or a, an independency structure to have a cause-effect structure to describe anything. So the difference between the big box and the little box is just the scale that you pick in order to try and articulate and model your system or explain your system. Interestingly, of course, those little boxes are all trying to do exactly what you are doing, trying to understand the boxology of the system at hand. But my main point is, are you not just stating that there is a choice here, that you have to pick the scale at which you want to characterize or model or understand or explain your system?
Excuse me. I don't think so. And the reason is that if the reason I suppose is that the notion of statistical independence that allows you to talk about things causally is itself an approximation that we get by assuming that the overall dynamics of the system is naturally multipartite. I mean, in the quantum language makes it easy to say, if to the extent that the whole state is fairly entangled, then the boundaries that we draw are completely artificial, and they can be regarded as boundaries only for a very short time until regarding them as boundaries no longer works. Whereas in a classical system, that's not true. I mean, in a classical system, all the interactions are causal, and any boundaries you draw really are boundaries. But from a quantum perspective, that's no longer the case, and the boundaries, staying boundaries, is only pragmatic, and that's independent of scale.
But I just briefly pursue that. So when I use the notion of scale, I included temporal scale. And what I hear you saying is that that certain carvings exist at specific scales. So at the quantum scale, the carvings are only valid as an approximation, possibly, over very, very short periods of time. But as you increase the scale, the duration where that boundary is in play in a classical or statistical sense extends. So again, one could argue that if you include separation of temporal scales in that scale invariance, then it's just a question of picking the scale you want to work at. And in a sense, that was my what I was driving at when asking you to think about the two ends of scales that we could consider, the moon and the electron, and why they are not relevant to biotic self-organization that is characterized by curious behavior and exploration and playfulness and sort of breaking of detailed balance, because you don't find that either at the quantum level or at the at the level of heavenly bodies, for example. So just to summarize, what I'm saying is that, yes, it is certainly true that statistical independences dissipate and fluctuate, and indeed a pullback attractor is itself a random variable. But over a certain time scale, they are in play, and that time scale increases as you increase the scale of the system.
Let's see. I suppose I would say that from a kind of a global quantum theoretic viewpoint, as you increase the temporal scale, the approximation of things being statistically independent always becomes worse. And the only question is how quickly it becomes worse, which is dependent on kind of density. well, dependent on energy density, that it always becomes worse. So I do think that the reason we see the world as classical at large scales is because we don't know how to look at it. We don't know the right way to look at it.
Yeah, I would also recall that you can do all, I mean, you can have all these visions from a time-independent manner and also a background-independent manner. So it's not only that you would choose the scale or you would choose a metric, you can literally let the cobordism tell you what the metric is or the homological class or the character. So you can definitely do all that with no time and with no particular conception of space besides
Right.
the one you're observing. And I guess this is what you were saying, no, Chris?
Yeah, right. Yeah, I think I think that we'll eventually be forced to consider space as um, something that we impose as observers. Spatial scales is something we impose as observers. I'd love to be able to make that more precise.